Okay, now what I want you to get from this with condensation and hydrolysis reactions is that in a condensation reaction we have two molecules that join together, such as in this case propanoic acid and ethanol, which is an alcohol, with the elimination of a small molecule such as H2O or HCl. Now the reverse of this process is hydrolysis. So if you know condensation, you should know hydrolysis. Now hydrolysis is effectively a reaction with water, but what happens is a molecule gets split with the elimination of a small molecule such as H2O or HCl. Now in this case we've got propanoic acid and an alcohol, ethanol. We're using heat and concentrated sulfuric acid as conditions, and they're going to join together with the OH and the OH getting eliminated, and when they join together they make this ester down here. Now the C double bond O, the carbonyl, comes from the acid, because we can see that up here, and so this side is the acid and this side is the alcohol with the single bond O. So in naming this, we name the alcohol first, which has got 2 carbons, and that's going to be ethyl. If it was 3 it would be propyl, if it was 4 it would be butyl, if it was 5 it would be pentyl, and so on. And we've got 3 carbons on this side. Now that would be propanoic acid, but it's the conjugate base, so we call it propan, and we just add on the word OIT. Okay, OIT. So that's the first kind of condensation reaction. Now we can make an ester in a similar way without using a catalyst, and again we're going to get the Cl, and in this case the H basically getting removed, and we're going to get this time 2 carbons with the carbonyl group, and that's going to go there. Just going to draw in all the H's here, and then we're going to draw in this time 3 carbons on the other side and draw in all the H's, and the small molecule that gets removed here is plus HCl, whereas in the previous one it was plus H2O. This one doesn't require a catalyst. Now when these join together we're going to have 2 carbons from the acid side, from the ethanol chloride. You see, notice the C double bond O, and we've got 3 carbons from the alcohol. So this one's going to be propyl, and we're going to name it after that there's 2 carbons. Now that would be ethanoic acid, or ethanol chloride in this case, sorry, and it's going to be ethanoate. Okay, so all I'm wanting you to get from this is how they join together. There's a lot of similarity. Now if we move on to another one, this really is just a big ester. There's 3 ester kind of joins, and we've got triglycerides. So we have an alcohol on this side, and this is glycerol. This is the alcohol that you always see that either is used to make a triglyceride, or it's the one that you can see reforming in a hydrolysis reaction. Now this is a large acid. Now these acids you could have 3 different acids joining, but in this case I'm just going to have 3 of the same. So there will be this acid here. Now in here we could have some double bonds, we could have a longer chain than this, it all varies. But anyway, if we join these together, we're going to have, now this is the alcohol side, so this is really just this molecule up here. I'm copying down again here. We'll have the single bond O, and so basically, this OH and this H go to form H2O, and that really just joins on here. So this goes from this O to this carbon. It gets a little tricky to draw it, but you just put CH2, and you're just really copying here. Now I should have put some H's around here. And if this was 3 different carboxylic acids, I'd just be copying them out differently here. But just for ease of showing this, I've just had them all the same. Now this is where you get such a thing as saturated and unsaturated fats from. Saturated have no double bonds, whereas saturated do have double bonds. So a saturated one would have all 4 carbons just having single bonds, where an unsaturated would have a double bond in there somewhere. And a way for testing for that would be to add, for instance, bromine water, and that should discolour, and the more bromine water you can discolour, the more double bonds there will be there, and that would go from orange to colourless. Anyway, what I really want you to get from this is showing how to join these two together to make this, which is basically your triglyceride because of the three ester links. And if we were kind of drawing something around the ester links, we'd do that, but there's three of them there. Okay, so once again, this is very similar to the ester reaction. We're just really joining to make an ester bond here, and that's done with the removal of waters. So there's three H2Os that get removed, each one H2O for each one. Okay, so that's triglycerides and how they join together and are formed. Okay, so we've already done ester links at the moment, and now we're going into amino acids. Now, again, I'm trying to show you the similarity in how things join. In this case, the OH here is going to basically make it so it can join together to make an amide link, and we're going to get one of the H's off here going. Okay, so really it's just joining these together. So we're going to end up with this kind of link here, and that's an amide kind of bond, or in this case we could call it a peptide bond because it's part of an amino acid. Now, dipeptide just means we get one of those and one of those joining together, two amino acids join together, and so it's di. So most of this is just me copying. So notice I'm just drawing the NH2 like that instead of like that. It's exactly the same, and I'll have a CH3 down there, so I'm just copying this out. And then I get to this. Now, instead of having the OH, I'm going to go straight across to the N and go up there. So it's just one of the H's that's still there. And then again, I'm just copying again. And come to there. Okay, so, and in this case, this is the amide link or the peptide bond. Now, notice I had the OH and H from here joining. I could equally have done it where I could have got rid of the OH from here and an H from there, and then just had this carbon here bond directly to that nitrogen over there. So that would be a second possibility that I could have drawn down here, but I'm not going to worry about that at this stage. Now, okay, now I was going to show you something else, but I'm going to leave that at the moment. So this is all just how things join together at the moment. And I'm hoping that you see that polymers are pretty much the same thing. Now, in condensation polymers, the similarity is that, well, in this case, on each of the monomers we need to have a functional group on each end. So in this case we've got a carboxylic acid on both ends, so it's a dicarboxylic acid, and we've got an alcohol on either end of this molecule. And we need that. If we just had one functional group on one side and no functional group on the other side apart from H's, that couldn't be a monomer. And it doesn't matter where I put the OH here, here or here, just the same as it doesn't matter if I put it here, here or here. I've just chosen to put it there, okay? So when I join this together, again I'm going to just be getting rid of the OH and an H on here, and then I'm going to join. And polymers can only join with either a ester link like that or a amide link like this. Now obviously if there's an OH it's going to be an ester link, and if there was, like down here I'm going to do one where it's got an NH2, that's going to be an amide link. So you can only get an amide link when there's a nitrogen present. So I'm just trying to get that straight. So basically a lot of this is copying. Now this is a polymer, so if we just do one repeating unit, I'm going to start here, so I'm just going to have that going directly up in the air and that going out, and then I come to here, CH3, CH3, C double bond O, O. Now I'm on to this next molecule, and I come to here, I might just change colour, and that's going to have an H. See, it doesn't matter that I put these H's up or down like that. And then we're going to come to here, I'll leave this H going up here, CH3, and then I come to an another carbon, and then I have an H, an H, because there's 3 carbons in a row, and then I come to an O, and then I'd carry on. Now, one of the things that's supposed to be a carbon, by the way, there. Now, one of the things that's tricky is knowing exactly how many O's to have in this. Now, we really are going to have, we've got an H2O getting kicked out here as well, by the way, for each bond. So we've got 2 carbonyl groups there, which is great, and we've got 2 single bond O's, and that's all we need. So if I was drawing the repeating units, that would be just 1 repeating unit. If I was drawing 2, I would just copy this all out again, okay? Obviously I could move that over and include that O, but if I did that I'd have to move this O to exclude that, because this O is part of the next repeating unit, okay? Now, this is a similar reaction. It's a condensation reaction, and it's, this time we've got the OH here, and that's going to get removed, and one of the H's from here. So again, this is a bit of a copying exercise. We'll have this, and then we're going to go to here, CH3, CH3, we're going to go along to here, and then we're going to go to the N. Notice the N, I'll put the H up in the air, and then we carry on. Got to draw in all the H's, 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 get bored with these, but there you go. And you've got an H going in the air. Now, at the moment, this is 1 repeating unit. This is the amide link, and I've got 2 N's in here, and I've got 2 carbonyls. If I was to put any more carbonyls or any more N's, that would be going into the second repeating unit. Obviously, if I needed to do 2 repeating units, I would just copy out this whole thing like a stamp and put it next to it. But at the moment, all I've been asked for is 1, and that is also with H2O getting removed. Now, still on polymers, is just some variety here. This is a similar one, but we've got a carboxylic acid, so if we join that together, we're going to get, now I'm just copying out these, there are 4 carbons in a row. We've got the carbonyl, and then I'm on to there, I'll just put in some H's, and now next door we'll just go to this. Now, if I just carry on drawing in some H's here. Now again, all I've done is I've removed this time a Cl and an H, so HCl has been removed, so I'm just joining here, and this is 1 repeating unit, and this is an ester link. If we go further down, again, I really want you to see the similarities between all these, the way you join them together. And I've got this, so we've just got 3 carbons, a lot of copying, and this, because there's an N, it's going to be an amide bond, and again it's going to be HCl that gets kicked out, and I'm just going to copy that all, that's what 3 carbons, 1, 2, 3, we go to an N, and there's just more H's joining in. So, and again, that's your amide bond this time, and that is 1 repeating unit. So that's really, they're all very, very similar in that respect. Now, very lastly, I just wanted to show for polymers that there is a possibility of just having 1 polymer. Notice that functional group is different from that functional group. So if I was to join this together, obviously it would be an ester link because I've got an acid and an alcohol. And let's have a look, there's 3 carbons, so I'll just do this. And so this is really exactly the same as up here, except I've got rid of the OH and an H from there. And then if I join this to the next door one, and let's see, 1, 2, just draw in some H's. This would be 2 repeating units now. And have I made a mistake there? No, there's 3 carbons, there's that, and there's this, and we carry on. So that would be 1, 2 repeating units. There's this black is for the first one, and this green one is the second one with a ester link. So this has come from one monomer, because the monomer has 2 different functional groups, whereas previously we had monomers where we had the same functional group on either side, so we needed to have a second monomer which had different functional groups in order for them to join together. Okay, so that's condensation reactions.